Hi there, chemists. Second video on balancing chemical equations. And here I'm going to do some examples. Okay, I've got them all ready. Let's just dive right in. Example number 1, hydrochloric acid, and because you don't know the formula for that yet, I put it here, HCl, reacts with magnesium to form magnesium chloride and hydrogen gas. Write a balanced chemical equation. First thing that we need to do is write a chemical equation, okay? So we need to identify the formula for all these species. What's the reactants? What's the products, okay? Hydrochloric acid reacts, okay? So that's a reactant, hydrochloric acid, and because we don't know the formula yet, here we go, it is HCl. Okay, that went away, that's good. Okay, so on the left-hand side, HCl, okay. Hydrochloric acid is an acid usually dissolved in water. You don't have the skill to know this yet, but I'm going to put an aqueous state there because it's dissolved in water. I'm going to leave a bit of space, okay? And the other reactant, hydrochloric acid, reacts with magnesium, okay? So it's saying it reacts with magnesium. Magnesium's an element all by itself. Its symbol is Mg. Okay, and if it's magnesium all by itself, it's got metallic bonding and it's a solid chunk of magnesium. Okay, to form, reaction arrow. Oh, I've slipped back to there. Reaction arrow. It's going to form magnesium chloride. Okay, magnesium chloride is an ionic compound. Magnesium's on the left-hand side in group 2. Chloride is over with the halogens on the right. We've got an ionic compound. So we've got these two ions. Okay, magnesium forms an ion of 2 positive. Okay, it's in group 2. It will always form an ion by losing 2 electrons and forming a 2+ charge. Chlorine will form chloride by gaining 1 electron. Okay, now a number of these are going to attract because they're oppositely charged until they've formed a neutral compound or in a ratio that fills an ionic lattice, okay? And because it needs to equal 0, I'm going to need 1 magnesium, which brings a 2+ charge, and I need 2 chlorides to bring a 2- charge down to 0. So the formula for magnesium chloride is MgCl2, okay? So what I might do is just erase those, get rid of my working there. Okay, I need a state on it. Ionic solids. Ionics are solids at standard temperature and pressure because ionic compounds have very strong attraction, the strongest bonding of all. So solid. Okay, what's our other product? Oh, hydrogen gas. Okay, that's just not simple one atom of hydrogen. Hydrogen's a diatomic. It is a covalent compound where it bonds to itself, and it's H2, a diatomic, 2 atoms bonded, and it's a gas at standard temperature and pressure. Because the only attractive force between 2 hydrogen molecules from our last module we know is dispersion forces, very, very weak. Not much holding it together, so it's a gas. Okay, I've got my correct formulas for each and I've got them in the right space. Now it is time to balance. Okay, what I might do is swap colors to help it stand out. All right, what have I got on the left-hand side? I might start with magnesium because why not? We've got 2 by itself. We've got magnesium and hydrogen by itself. So one doesn't really have an advantage. Let's go magnesium. I've got 1 on the left from the magnesium and I've got 1 on the right, 1 in magnesium chloride there. So I'm all good so far with magnesium. Okay, let's take a look at chlorine. I've got 2 here, 2 in the 1 molecule of magnesium chloride, and I've got 1 here in the hydrochloric acid. So if I want 2 on the left-hand side, I've got to increase it by adding in another hydrochloric acid molecule. Okay? Now I have the 2 chlorines on the left-hand side. All right. So magnesium is balanced, chlorine is balanced, hydrogen is the one left. Okay, I have now got 2 hydrogens on the left because I've got 2 hydrochloric acid molecules, and I have 2 on the right because I have 1 H2 molecule or 1 hydrogen molecule there. So I'm balanced there as well. Okay, what I'm going to do now is, because I know I'm balanced, I'm going to rewrite it with my stoichiometry on there. So HCl plus HCl gives 2 HCl aqueous, and I've got 1 atom of magnesium. I was about to say sulfur, embarrassing. S for solid, not sulfur. I have 1 ionic base unit instead of molecule of magnesium chloride, and that's a solid, and 1 molecule of gas, a covalent molecule there. So it's a 2-to-1 reactants, 1-to-1 products reaction. All right, let's do another one. When sodium bicarbonate is heated, it decomposes to form sodium oxide and carbon dioxide and water. Write a balanced chemical equation. Okay, first we're going to figure out what are the reactants and the products and start doing formulas for them. So when sodium bicarbonate is heated, it decomposes. Decomposition reactions take one thing and it does something, like is usually heat, and it forms more than one product. So we've only got one reactant here, the sodium bicarbonate. Okay, it's also known as sodium hydrogen carbonate. So it's the ionic compound, because we've got a metal and a non-metal. Sodium is a metal. The carbon and the oxygen in the carbonate and the hydrogen in the bicarbonate all together is non-metals. So we've got an ionic compound, sodium plus, and the bicarbonate ion is HCO3 single minus. Okay, because we've got a single plus and a single minus, they react and, they don't react, they attract in a 1-to-1 ratio. So the formula for sodium bicarbonate is NaHCO3. And notice we don't put a bracket around the polyatomic ion because there's only one of those bicarbonate units there. Okay, there's only one, so we don't put the brackets. Now, because it is an ionic compound, standard temperature and pressure, it's a solid. And if you've done a bit of baking, you know that it's a solid white powder, used a lot in baking. All right, I'm just going to erase a little bit of my working there so it doesn't get confused. Okay, as I said, we've only got one reactant because it's a decomposition reaction. So it's just the sodium bicarbonate decomposing when we heat it to form more things. Sodium oxide, okay, that's sodium is metal, oxygen is a non-metal, so we've got an ionic compound, and the sodium ion, as we said before, is in group 1. Oxide, IDE, is a monatomic ion. It's just the ion of oxygen. Go to oxygen on the periodic table and you'll see it's in its group 16, or it's in the group that has ions that gain 2 electrons. Okay, O2 minus. So sodium brings 1 plus, oxide brings 2 minus, so I need 2 sodium for 1 oxygen. Na2O, okay? Get rid of that. Ionic compound at standard temperature and pressure is going to be a solid. What else do we form? Carbon dioxide. Okay, carbon and oxygen, non-metals, so we've got a molecule, a covalent molecule, 1 carbon dioxide means CO2. And that's a gas. Should be quite familiar with that one. It's causing a lot of trouble, and hopefully you know good old water, subscript L for liquid. Oh, did I leave enough space to do my balancing? Let's see. Okay, red pen. Let's do a bit of balancing. Where are we going to start? We're going to start with sodium. We've got 2 here from our 1 base unit of 1 ion of Na sodium oxide. So I've got 2 there, so I need 1 more on the left hand side, so I need to add in more sodium. I can only do that by adding in a whole nother molecule of sodium bicarbonate, okay? I can't do anything else there. All right. Okay, hydrogens. I have 1, 2, because I have 1 from each sodium bicarbonate, and I have 2 here because I've got 1 molecule of water, H2O. So that's all good. Okay, what have I got left? I might do carbon now. I've got 1 carbon in each sodium bicarbonate, so I've got 2 on the left. I need 2 on the right, and each carbon dioxide has only got 1, so I need a whole nother carbon dioxide. Okay, a second one there. Now I've got 2. Okay, finally, I need to count my oxygens. I've got 1 in the sodium oxide. I've got 4, 2 for each carbon dioxide there, and I've got 1 over here, okay, and 1 in the water. So all up, that's 6. Here on the left-hand side, I've got 3 in each sodium bicarbonate, which also makes 6. So I'm balanced, okay? What I'm going to do is rewrite it underneath and put the stoichiometry out the front. So 2 lots of sodium bicarbonate, and I've got 1 lot of sodium oxide, and I've got 2 molecules of carbon dioxide, so big 2 out the front, and I've got 1 water molecule. All right, all completely balanced. Oh, example 3, I've got 4 of these little ones in here. Let's see how we go with just putting the numbers out the front now, okay? This top one here, one thing that I noticed from my bag of tricks is I've got oxygen by itself there. I'm going to deliberately leave oxygen to last. I've got carbon, hydrogen, and oxygen here, so I'm going to do carbon and hydrogen first, leave oxygen to last, okay? On the left-hand side, in the C2H6, I've got 2 carbons. On the right-hand side, I've got 1 carbon with 1 carbon dioxide. So I need another carbon dioxide to get my 2 on the right-hand side. So I'll put a 2 there, temporarily maybe. I might need to change it, but I'll put a 2 there. Okay, I've done my carbon, I'll do my hydrogen now. I've got 6 on the left-hand side because I've got 1 molecule of C2H6. I have got 2 on the right-hand side because I've got 1 molecule of water. So to get the 6 on the right-hand side, I need 2 more waters. 2, 4, 6. So I need 3 waters all up. So I'm going to put a big 3 in front of the water. Okay. Now I've got my oxygens left. Okay, and this is going to be good because it's going to show you another trick with fractions. I'm jumping ahead, spoilers. Okay, I've got 2 on the left-hand side from the O2. I have, okay, there's 2 in each carbon dioxide, and I have 2 carbon dioxide. So that's 4 there, right, a little 4. And I've got 1 for each water, and I've got 3 waters, so that's 3. So I've got 7 all up, okay? 7 all up on the right hand side, but the trouble is I can only add O2s on the left hand side. So a trick that you can do is go, well, if I want 7 all up and I've got O2, I want 7 halves of an O2, okay? Tricky, adding in a fraction there, okay? 7 halves of O2 is 7 atoms of oxygen. And that's what I've got on the right-hand side. I've added my fraction in. Now, you could leave it here. It's a little bit messy. But what we do as chemists, we want to get rid of that 2 in that 7 halves fraction. And to get rid of that, and to keep the same ratio, we multiply all the stoichiometry by 2. Okay? So in front of them, the C2H6 is a 1, so if we're multiplying it all by 2, there's a big 2 in front there. And if we multiply 7 halves by 2, or 7 on 2, we get rid of the 7 on 2, and it just becomes 7. That's a bit messy. And now we're multiplying by 2, and this goes to 3. And so the 3 waters now turns into 6 waters. My messy writing. And the 2 carbon dioxides multiplied by 2 become a 4. Okay. One other tip here is, one final thing you can do is to make sure that there's no common divisor between all these ratios, all the stoichiometry. Is there a common divisor with 2, 7, 6, and 4? No, there isn't. If that 7 hadn't been there, though, 2, 6, and 4 have a common divisor, which is 2, so you can divide it all by 2. But 2, 7, 6, and 4, that's the lowest common factor for all those common ones. If you just leave those numbers there. That was a good one. I like that one because we left the oxygen to last, and we also used that fraction trick. All right, the next one here. Oh, this is a good one because I'm noticing I've got a nitrate here, and that's actually nitric acid. I've got 1 nitrate there, and I've got this boron nitrate here. So there's 3 nitrates there according to the formula. When we've got polyatomic ions, instead of splitting them up, treat them as one whole unit, okay? So what I'm going to do here is I might as well start with this. I've got 3 nitrates on the right-hand side. I've got 1 on the left. I want 3 nitrates on the left. So to get 3 nitrates, I need 3 whole molecules of this HNO3, or nitric acid we call it. You'll learn that later. Okay, that balanced my nitrates out. What I might do is balance my bromines out. I've got 6 on the left. I want 6 on the right, and each HBr, or hydrobromic acid, brings 1, so I need a big 6 out the front. I want 6 molecules of that. Okay, I balanced my nitrates. I balanced my bromines. I need to balance my borons, okay? I've got 2 on the left, but I've got 1 on the right, okay? I'm going to need to have 2 boron nitrates there, okay? But now I've ruined my nitrates, okay? Now instead of 3 of them, I've got 6 of them, because each boron nitrate brings 3, and I've got 2 molecules of it. So I've got 6 nitrates, so I'm going to have to change this one over to 6. And we'll see how we're going now, okay? So I balance my borons, I balance my bromides, I balance my nitrates, I've just got my hydrogens left. I've got 6 molecules of HNO3, so I've got 6 H's on the left. And over here, I've got 6 molecules of HBr, so I've got 6 atoms of H on the right. So I'm all balanced now, okay? So the numbers in front of these, or because there's a space there, I'll put a 1, but technically we don't. So 1 molecule of B2Br6 reacts with 6 molecules of the HNO3, or nitric acid, to give 2 molecules of boron nitrate and 6 molecules of hydrobromic acid, HBr. Next one, selenium chloride and oxygen react to give selenium oxide and chlorine. Oh, where are we going to start? We got oxygen by itself and we got chlorine by itself. Why don't we start with selenium? Left, we've got 1. Right, we've got 1. Oh, that was a nice, easy start. Okay, don't get in a false sense of security. 6 chlorines on the left and 2 on the right. Okay, I need 6 on the right, so I need to bring in another 2 chlorine molecules to have 3 all up, so a big 3. That will give me the 6 chlorine atoms on the right. Okay, now we've just got oxygen, and there's 2 from the selenium oxide, and there's 2 on the left from 1 molecule of oxygen. So I'm all balanced. So it's a nice 1-to-1 reaction to give 1-to-3. Okay, let's look at this arsenic reaction. Arsenic and sodium hydroxide makes this, I'm guessing, sodium arsenate. I could have that wrong. But this sodium arsenic and oxygen thing, and hydrogen gas. Okay, let's balance arsenic, because why not? Okay, 1 on the left and there's 1 on the right here in this molecule. That was a nice easy start. Okay, 3 sodiums on the right, but I've only got 1 on the left, so I need 3 sodium hydroxides. 3 molecules of sodium hydroxide to balance out those 3 sodiums. Okay, sodium and arsenic are balanced. I need to balance my oxygen and hydrogen. Oxygen, I've got, in sodium hydroxide, there's 1 oxygen and I've got 3 molecules of it. So I've got on the left-hand side 3 oxygens. And on the right-hand side, in this 1 molecule, I've got 3 oxygens. So I'm balanced with my oxygens. I've just got hydrogens left. Okay. I've got 1 hydrogen for every sodium hydroxide. So I've got 3 hydrogens on the left. And I've got 2 on the right. Okay. To get 3 on the right, I need 3 halves of it. Okay. 3 halves of H2 are 3 atoms of H2. So I'm putting in that fraction stepping stone. Okay. 3 on 2. I want to get rid of that fraction now. 2 is on the denominator, so I'm going to multiply all my stoichiometry by 2, okay? So I need 2 arsenics, and I've got 3 sodium hydroxides, so I'm going to multiply that by 2 to make 6. And I'm producing one of these sodium arsenates. Well, multiply that by 2. I'm producing 2 of those. And 3 halves of the H2 multiplied by 2 is just going to equal 3 molecules of your H2. Another fraction stepping stone one. Okay, I think that might be it. Yeah, we've got a nice worksheet to do there. There's 4 videos that will take you through it. A good Ted Ed one, and then some Tyler DeWitt and lovely Professor Dave. A worked example, and you can do check your understanding. And we've got a couple of little practicals to do. I'll go through those in a separate video one day. Conservation of mass with 2 reactions there. And also the decomposition of water, which shows a good molar ratio. Okay. Next video, I'm going to introduce you to one of the biggest concepts here, the mole. See you next time.